Okay, so here we are looking at method 2. Method 2 is saying apply a known external force tangential to the rim of the initially motionless platform. Measure the change in angular velocity as in method 1. Also measure the radius of the platform or some other valid measurement of lever arm. So this is going out of an approach where we are saying, I'm going to switch this over really quick, where we are saying that the net torque, not the highlighter, that the net torque is equal to I times alpha. So we're saying in this case that our torques are going to be made up of some sort of positive torque that we're applying, and then we have this negative frictional torque. And sorry if I mess up the directions of those. But so we have a positive, what we're going to call applied torque, so I'm going to call that torque applied, minus our frictional torque is equal to I times alpha. And then what we want to say is go a little bit further and say, well, alpha is hard to measure. So what we're going to do is we're going to calculate alpha by doing what we did in method 1. So in method 1, I'll tell you how we did it in a second, but we're measuring the change in angular velocity. So this will be our final equation. We know the rotational inertia. So the rest from there is going to be quantities that we can measure in order to find this frictional torque. And then just going one step further, with the applied torque, we can't really measure a torque. We're going to have to calculate a torque. So we're going to calculate it by doing some known force at some known radius minus this torque friction equal to I, and then our change in angular velocity. So this is going to be what we're arguing from. This is kind of the thought process of method 2. Now that we know the thought process, I just want to go through and explain what our free response will look like. So the first question that they ask is what quantities would be measured. So we want to measure just everything that we just argued. We want to measure force. We want to measure radius. We want to measure then this angular velocity and time. So with the angular velocity, what we did in the last case, what I said that the easiest way to do this, again, angular velocity is a very hard quantity to measure. What I said in the last video for the method 1 people was, yeah, maybe you thought we could use this rotary motion sensor, but the problem with that is there's a lot of friction in here. So we're introducing a lot of forces and a lot of torques that we don't want as part of our experiment. We just want to know about the torque in this disk. We don't know about the torque in here. So this is probably not our best bet. So what I told them, the easiest way to do this may be to set up like a video camera up here. So set up maybe like we can pretend that we have access to a slow motion camera, right? Like the iPhone has a pretty slow motion camera. Place some sort of dot here. And then what we'd be able to do is analyze this video footage and figure out every time it went 2 pi radians, how much time did that take? So really what we're measuring is time, and then that will give us angular velocity data. And we could do that for some other time. And that will give us another set of data for angular velocity. So really what I'm going to say is just we can measure time and then some sort of way to count radians. I'm just going to say that we measured it. I don't know if the College Board would want that or not because we're not technically measuring radians. We're just saying we have 2 pi radians. But we'll address that in our procedure. So this one, I don't think we actually need it. So then what equipment would be used for the measurements and how would that equipment be used? So for force, before we've used like a force probe, one of those like kind of looked like that and had the little hook on it. We have one of these force probes, these force meters to measure force. So I'm just going to list out everything that we've done. So force, we can use a force probe. I don't even know if that's what that's called. I think I just call it that. And then radius, we know that we can measure a radius in meters with a meter stick. And then we can measure time with a high-speed camera. We can say we can count frames. Cool. All right, so measure center to radius to outer edge. And then we say apply horizontally, or I guess perpendicular to disk. All right, so we're looking at parts A and I. We will get a point if we indicate valid measured quantities. We did that. And then a list of equipment and a plausible way to measure the quantities. Cool. So we have done those in this part. Cool, cool, cool. And I'll put in read on computer. Okay, so now we're going to talk about the procedure and kind of what steps we're going to take. So this is a little bit difficult. I want to show you what they want first, and then we'll go ahead and do it. So they want a procedure that's consistent with what we're measured, so we're only allowed to use quantities that we measured, that we said that we're going to measure. So we have to set up a procedure. If it says anything else, then we have to go back and change what we wrote before because we can only use quantities that we measured. For a plausible procedure that could be used to experimentally determine frictional torque, and then for talking about experimental uncertainty, so this will be at the end, we can talk about, hey, do some trials. So let's try it out. I'm just going to switch to this typing really quick because I don't want to write out a procedure. So let's try it. So step one is let's set up a slow motion camera directly over the disk. Then we can place a small dot on the edge of the disk so we can tell when the disk has made a complete rotation. So kind of like we did that tape on the bike wheel, this will tell us when we've made a complete rotation. We'll be able to reference that dot. So I'm going to call it like a reference dot. And then for this part 3, we want to make sure that the disk is initially at rest. So to a disk that is at rest, hook the force probe at the edge of the disk and spin the disk using the force probe. Make sure that the force probe is held perpendicular to the edge of the disk. Press record on the force probe software as you begin torquing. I don't know if that's the right word. And then before that, I forgot to say, use a meter stick to measure the radius of the disk from the center point to the outer edge. And then, yeah, we'll just say force the disk for as long as you can and stop forcing the disk. So that's what we got to do. So we got to spin it up. Honestly, I kind of want to go back and change the procedure. We could say something about like wrapping a rope around the disk. So we say wrap a rope around it, and then if we're looking at this overhead view, we can pull on it with the force probe, and that may be a little bit easier for us to get like a more constant force, but I'm not going to change my procedure. But it may be a little bit easier if we do something like that. So if this is like my overhead view, so yeah, so say something about wrap a string around it and then make sure that we're forcing it. So that's our procedure. That's enough that we could replicate it. And then the last thing we can do is say perform another set of 5 trials. We'll just go crazy with it. We'll say that we're 5. We probably wouldn't do 5 in real life, but we're not actually doing it. We're just pretending that we're doing it. So that checks out. Describe how the data could be used to determine the frictional torque on the platform. So this is really what we said before. So this is you going through and talking about your equation and what you're doing. This is typically a point where you would just show some math and say how you got that data. But so we would say that we know that our net torque is equal to our force times our distance from the center minus our frictional torque equals I times alpha. So we'd say this is the force that we're using, this is the radius that we measured, and then we could talk about how we got our alpha data by doing, so we say something about, hey, we measured that we went 2 pi rotations for some amount of time, then we 2 pi rotations for some amount of other time, so we counted frame data on slow motion camera to find a complete rotation. And then we'd say that we measured, and then we use the time values to get the rotational velocity. So that's how we got those. And then this, we could talk about how we looked at the computer values at corresponding times. At T1 and T2. And then we can talk here about how we just used our meter stick. And then we'll just kind of solve out that equation. We said that our angular acceleration is equal to our change in angular velocity. So we say 2 pi over T2 minus 2 pi over T1 divided by the change between them times I is equal to F R minus T friction. And then if we solve that out, we could plug data into there and we would be able to, so this is like T2. We could plug our data into there and we would get a value for that frictional torque. And then this last part is kind of an experimental uncertainty piece where we are looking to see, hey, maybe this depends on the speed. Did we take speed into account here? In this case, we did. Our equation depends on this omega 2 and omega 1. So the part where we measured theta over time got us our angular velocity data. So it did depend on that. If we look at our key, for correctly relating the procedure in parts A to the assumption of whether or not it's dependent on speed. So we did that, and then connecting the analysis to angular speed. We need to do that really quick. Or no, sorry. So yeah, we measured this and we said that told us about our angular speed. And then briefly describe how we can do it. All that we'd say is we'd have to measure or do more trials at different angular velocities. And then if the torque friction, if it changes, then we know that it depends on our angular velocity. So if we do more trials and if we do them and we see, hey, every single time we do this and we're taking different angular velocity data, we get a different frictional torque, then we know that it depends on our angular velocity. If it's constant, then it does not depend. That's not the right symbol for that. Doesn't depend. That's not a symbol either. On angular velocity. All right, so that was method 2. Hopefully that was okay. Sorry that was a lot, but hopefully it's helpful to see the keys and go from there. Yeah.